All right, picking up on the second half of the section 2-3 lecture, I do have a correction for the last page, or excuse me, for page 4. This very first problem, I just forgot how to math there for half a second, and it cost me. Everything was fine until I tried to do this multiplication. 5 times 15 is 75, not 65. 65, negative 65 plus 75 is positive 10. So that means there is a remainder of 10. So everything stays the same except we just tack on that plus 10 down here. Everything else looks good. So next page, we're going to evaluate the polynomial. P of x is, and this polynomial, P of x here probably looks familiar, Q of x probably looks familiar, because we've dealt with these already. But we haven't evaluated one. So let's follow the directions here. All the x's get swapped out for negative 1s. I got to do the powers first. So negative 10 times negative 1 squared is positive 1. Plus 2 times negative 1 cubed is negative 1. Negative 10 times 1 is negative 10. 2 times negative 1 is negative 2. And then minus 5 is minus 5. Negative 10 minus 2 more is negative 12. Minus 5 more is negative 17. All right, next, Q of x. 2x cubed minus 7x squared minus 65. All the x's get swapped out for 5s. Parentheses are critical here because I expect this is going to be done on a calculator. And if you don't put the parentheses there, you're opening yourself up for some errors. So that is 5 cubed is 125. 5 squared is 25. 2 times 125 is 250. 7 times 25 is 175. 250 minus 175 is 75. And then 75 minus 65 is 10. So Q at 5 equals 10. And then lastly, got a long one here. R of x is, as reads, as you can see there, what is R at 2? So that is 2x to the 5th. All the x's get swapped out for 2's. So that's 13 times 2 to the 4th minus 3 times 2 cubed minus 58 times 2 squared minus 20 times 2 plus 24. If you just enjoy doing these by hand, all the powers go first. 2 to the 5th is 32. 2 to the 4th is 16. 2 to the 3rd is 8. 2 to the 2nd is 4. 2 to the 1st is 2. And then the constant is 24. Now do the multiplication as you encounter it from left to right. 2 times 32, 64. 13 times 16, 208. 3 times 8 is 24. 58 times 4 is 232. I had to want that one. 20 times 2 is 40. And then plus 24. Do the math, work it all out, and turns out this all adds up to 0. So R at 2 equals 0. Now, I said these should look familiar because if I go back a page to my synthetic division example, I had this problem, 2x cubed minus 7x squared minus 65 divided by x minus 5. and I found a remainder of 10. When I evaluate this problem, 2x, the q of x here, 2x cubed minus 7x squared plus minus 65, when I evaluate that at 5, I get 10 out, right? So 5 went in my little box, and when I did synthetic division on the quadratic that I just evaluated, my remainder and my evaluation turned out to be the same number. Let's see if that happens somewhere else. Okay, here's the polynomial that was out of order. 2x cubed minus 10x squared minus 5 divided by x plus 1. In that one, I'm testing out -1. I do my synthetic division. I end up with a remainder of 17. I evaluated p at -1, and I got -17. Those match up. Same thing's going to be true for r of x down here as well. And the reason for that is the remainder theorem. The remainder theorem says just exactly what it just gives rule to what we just discovered or what we just saw, this pattern. If a polynomial f of x is divided by x minus c, the remainder is f at c. Okay? That means the remainder is the same as the value that the polynomial returns if you plug c in to it. So let's do one more. Let's kind of drive this point home. Here's g of x. Evaluate g at 2. Well, g at 2 means swap everything, swap out all the x's for 2's. So that is -3 times 2 to the 5th plus 2 times 2 to the 4th plus 6 times 2 squared minus 2 plus 4. 2 to the 5th is 32. 2 to the 4th is 16. 2 squared is 4. 2 is 2. 4 is 4. -3 times 32, -96, plus 32, plus 24, minus 2, plus 4, and I find that this comes out to, when I plug it into the calculator, -38. So g at 2 is -38. All right. So if the remainder theorem is true, when I try to divide g of x by x minus c, which is the number that I plugged in for x, so c is 2. When I try to divide by x minus c, the remainder that gets left from that synthetic division will match the evaluation of g at 2. So I'm dividing, and yes, you can do this long. You can do this long division. I prefer synthetic. But in both cases, I need to make sure I have all the terms. I don't have an x cubed term, so I need to put that 0 there as a placeholder. And I'm dividing by x minus 2. Okay. Well, if I'm dividing by x minus 2, first step, take the divisor, set it equal to 0, and solve. X is 2, So that means 2 goes into the box, and then the coefficients of the polynomial start with -3, 2, 0, 6, -1, and 4. Drop the -3, multiply by +2, that gives me -6. Add 2 plus -6 is -4. Multiply -4 times 2 is -8. 0 plus -8 is -8. -8 times +2 is -16. 6 plus -16 is -10. -10 times 2 is -20. -1 plus -20 is -21. -21 times 2 is -42. 4 plus -42 is -38. And look at that. There it is again. So why is this useful? Well, it's useful because, honestly, once you get the hang of it, synthetic division is easier than evaluating long polynomials, especially for values of x that are larger. So that is an example of where if I do the long division, if I need to evaluate a polynomial, I can use synthetic division and get the remainder. Or if I've already performed synthetic division, I can tell you what the value of that function is going to be when you plug in the value, or in this case, when you plug in 2, I can tell you g of x is going to return 38. All right, so finish that up. We've seen how the remainder theorem tackles evaluating polynomials. So we're going to use the remainder theorem and determine the remainder when f of x is divided by each factor. So I've just got one function here, and I'm going to be dividing it by all different factors. So we're going to take this to synthetic. So for all of these, let's see what actually goes in the box. If I'm dividing by x plus 1, what I'm doing is I'm checking, is -1 a 0 of the function f of x? Okay. For x minus 3, you probably won't have to keep writing this stuff out. I'm checking if 3 is a 0. For x minus 4, I'm checking if 4 is a 0. And for the last one, and there comes a fraction, I'm checking if 5 halves is a 0. All right. I'm also, this process is allowing me to do the same thing. I can either plug -1 into the original function and see what value I get out, or I can divide, I can do division of f of x divided by x plus 1, and whatever I end up with for the remainder is the same value that I would get if I just evaluated the function at -1. All right, so bring that 2 down, and I do this in red typically, so let's do that. And I'm just going to stick with one color right now. 1 times 2, -2. 1 plus -2 is -1. -1 times -1 is 1. -49 plus 1 is -48. -48 times -1 is 48. 79 plus 48 is 127. And then negative 1 times 127 is negative 127. 15 plus negative 127 is negative 112. All right. And the problem says use the remainder theorem to evaluate. That's all I'm going to do. So what does this mean? This means if I plug negative 1 into f of x from up here, I'm going to get negative 112. That's going to be my output. Okay. If you want to check it quickly, you can always put it into Desmos. And let's see if we're right. So in Desmos, I've already typed in f of x. And now I'm going to check what happens when I plug negative 1 in. When I plug negative 1 in, I'm evaluated at negative 112. All right. All right, so let's do the next one. X minus 3. I'm checking to see if I divide x minus 3 into f of x, what's going to happen? I'm checking out the number 3. All right, not sure what's going on now, but I think I fixed it. So let's finish up these remainder theorem problems. X minus 3 divided into f of x. Convert to synthetic. 3 goes in the box. Coefficients are the same as above, so I can just copy those. 2, 1, negative 49, 79, 15. Bring down the 2. 2 times 3, 6. 1 plus 6 is 7. 7 times 3 is 21. Negative 49 plus 21, negative 28. Negative 28 times 3, negative 84. 79 plus negative 84 is negative 5. Negative 5 times 3 is negative 15. 15 plus negative 15 is 0. So what does that mean? That means if I plug in 3 into my function, I get 0 out. Now, that means for our division, that means x minus 3 divides into f of x evenly. If I go to the graph, f at 3 is 0. That's a useful piece of information because what is that? That is an x-intercept. So take a look at the graph and take a look right there. See that x-intercept at 3, 0? So it turns out when I do synthetic division, I'm actually determining if the value in the box is a 0 or not, right? If it's a 0, the remainder will be 0. If it's not, the remainder will be something else. All right, next, x minus 4. X minus 4. So I'm checking if 4, you can think of it two ways. I'm dividing f of x by x minus 4, or I'm checking if 4 is a 0 of f of x. Again, coefficients remain the same. Two times 4 is 8. 1 plus 8 is 9. 9 times 4, 36. Negative 49 plus 36, negative 13. negative 13 times 4, negative 52. 79 plus negative 52 is 27. 27 times 4 is 108. 15 plus 108, 1, 2, 3. So that means if I take 4 and plug it into the function, I get out 123. And then the last one, because everybody loves fractions so much, I'm checking 5 halves. That goes in the box, and you can do this. Okay. Other coefficients stay the same. 2, 1, negative 49, 79, 15, and draw our line, change our pen, 2, and then we get to do the math. 2 times 5 halves. That worked out nicely. That's 5. 1 plus 5 is 6. 6 times 5 halves is 30 over 2, which is 15. 49 plus, negative 49 plus 15 is negative 34. Negative 34 times 5 halves is negative 17 times 5, which is negative 85. 79 plus negative 85 is negative 6. Negative 6 times 5 halves is negative 15. 15 minus 15 is 0. And so I have found that f at 5 halves is 0. And again, what does that mean for my graph? That means that there's an x-intercept. When I plug in 5 halves for x, I get y is 0. The only place where y is 0 is on the x-axis. So there's another root, or there's another 0. All right, so remainder theorem done. Now we're going to move on to the last topic from 2.3, which is the factor theorem. The factor theorem simply says if f at c is equal to 0, then x minus c is a factor of f of x. And then it goes the other direction too. If x minus c is a factor of f of x, then f at c is 0. We've run into this already when we do synthetic division and I get a remainder of 0. That tells me that the corresponding binomial goes into f of x evenly. So we're not really changing anything. We're not adding anything to it. We're just now paying attention to, is the remainder 0 or is it not 0? If the remainder is 0, then I've actually figured out a way to break that polynomial down into its one binomial, and in this case, a trinomial, or excuse me, a third degree polynomial. Let's just get into an example here and see what you think. Use the factor theorem to determine if the given polynomials are factors of f of x is equal to 2x to the fourth minus 13x cubed, plus 10x squared minus 25x plus 6. I'm testing x minus 6. So remember our rules here. X minus 6 corresponds to a 0 of 6. Okay, so I'm figuring out if I plug 6 into f of x, what do I get back? All right, so 6 goes in the box. Coefficients come to play. 2, negative 13. Keep an eye out if we're missing any. Fourth, third. Don't know why I wrote a positive there. Second power. first power constant. Bring down the 2, multiply. 6 times 2 is 12, and then it's just add. Negative 13 plus 12 is negative 1. Negative 1 times 6 is negative 6. 10 plus negative 6 is 4. 4 times 6 is 24. Negative 25 plus 24 is negative 1. Negative 1 times 6 is negative 6. 6 plus negative 6 is 0. I got a remainder of 0. So that means I now know, because of this, that if I take f of x and I plug in 6, I will get an evaluation at 0. The factor theorem says if I know this to be true, then it says x minus c is a factor of f of x. And that's the factor theorem. That's what it does. Okay? You can use it in both directions. In this case, I found a remainder of 0, which means that if I evaluate the function at 6, I get a remainder of 0. So that means when I plug 6 into the function, I get a 0, or I get 0. Next is x plus 3. Remember the game. That means, what am I looking at? Negative 3. So there's negative 3. Coefficients stay the same. Negative 25. 6. Bring down the 2. Negative 3 times 2. Negative 6. Negative 13 plus negative 6. Negative 19. Negative 19 times negative 3 is positive 57. 10 plus 57 is 67. 67 times negative 3, negative 201. If you think this is going off the rails, or you think, oh, these numbers are getting too big, you'll be surprised. This one's not going to work, because right there it goes crazy. Negative 226 times negative 3 is 678. 678 plus 6 is 684. So f at negative 3 is equal to 684. So x minus, it'd be x minus negative 3, which becomes plus 3, is not a factor of f of x. All right, so that's the factor theorem. That's what it does for us. I do synthetic division, I do long division, I find the remainder, and then that tells me how the original function would evaluate. So next we have, and the notes are just a slight, they're forgetting just a couple words. Here we go. So first thing I want to do is factor f of x, given that negative 5 is a 0 of f of x. All right? So I know negative 5 is a 0. So if negative 5 is a 0, if negative 5 is a 0, then x minus negative 5 is a factor of f of x, right? So the x minus negative 5 becomes plus. So if x plus 5 is a factor, then I'm going to set that equal to 0 and solve. There's the negative 5 going in the box. Coefficients, 3, 25, 42, negative 40. So why would I still do synthetic division here? Well, because it's a cubic. So I'm starting out with a cubic. It doesn't have any special form about it. But I know that negative 5 is a 0. If negative 5 is a 0, then x plus 5 divides into it. So that's what I'm going to do here. I'm taking f of x, I'm dividing it by x plus 5. And bring down the 3, multiply, that's negative 15. 25 plus negative 15 is 10. 10 times negative 5 is negative 50. 42 plus negative 50 is negative 8. Negative 8 times negative 5 is 40. 40 plus 40 is 0. Now, remember, the results of this are what? All but the last number at the bottom of the synthetic division are coefficients to the quotient, right? So if those are coefficients to the quotient, what powers do they have? This started out as a cube. This was 3x cubed. Remember, if I do synthetic division, it's always going to drop the power by 1. So that's 3x squared plus 10x minus 8. That's my quotient. All right. So I have taken f of x, and I've actually broken it down into my divisor, which is x plus 5, times the quotient, 3x squared plus 10x minus 8. All right? Am I factored all the way yet? No, not yet. I got 3x squared plus 10x minus 8. Can I factor that more? Probably. Let's come out here to the side and deal with it. If I'm going to factor this just an old-fashioned way, I would deal with bottoms up. You can probably guess and check this one if you really, really want to. But let's just do something we know works. Bottoms up. Bottoms up takes a and c and multiplies them. 8 times, and negative 8 times 3 is negative 24. Does this factor two things multiply to negative 24 and add to 10? Yes, it does. That is negative 2 and negative 12. And then we have to remember, once you have found that, then you divide those constants by whatever a was in the beginning. So that leaves me with x minus 2/3 times x minus 12 divided by 3 is 4. And now I have f of x is equal to x plus 5 times 3x squared plus 10x minus 8 breaks down into x minus 2/3 and x minus 4. All right, so the first step in there is the new material, and then that bottoms up procedure, the breaking down that quadratic into two binomials. That's old material. That's stuff that is in the past and should already have been mastered. All right, so why would I want to do that? Because look at the next question. I'm asked to solve that cubic for when is this 0? Solve this equation. Here's the cubic. Third degree polynomial, set it equal to 0 and solve. Well, I already know that 3x cubed plus 25x squared plus 42x minus 40 is the same thing as what I just wrote above. x minus 4 equals 0. Right? And why is that great? Because I've got the zero product principle here. If I'm multiplying stuff and the result is 0, then one of them has to be 0, or all of them are. So when I break this down, and technically you use the zero product principle twice here. You just say, we pretend like, oh, this is one thing, and then this whole is one thing. So then this is 0, or this is 0, and then this is 0 means they break up evenly, if you want to get technical. But I don't think anybody's going to be bothered by that. So I now know that take x plus 5, set it equal to 0 to solve. Take x minus 2/3, set it equal to 0 and solve. Take x minus 4, set it equal to 0 and solve. All right. And we were asked to solve this. So what are my solutions? They are not x equals -5, x equals 2/3, and x equals 4, because those are vertical lines. The solutions to this equation are, and then you just list all of the numbers. X minus 4. Did I do that right? Oh, look at this mistake. Larry, no. All right, so multiply to -24, add to 10. So this is negative. This is actually positive. That's my fault. Oh, no. I messed it up real good, didn't I? Or no? Which one is it? Let's come back to that. Here, let me get back here. Get my stuff together. That breaks down into multiply to -24, add to +10. So plus 12 minus 2. That's better. And then we come back, and then we come through and deal with that division. So x minus 2/3, and that's x plus 4. So x plus 4 equals 0, plus 4, plus 4, and x is -4. That's better. All right, so what are my solutions? They are -5, -4, and 2/3. Always a good idea to check your answers, because missing a sign or something like that is very easy to do. All right, and then the next skill practice problem, f of x is 2x cubed plus 7x squared minus 14x minus 40. And you were told that -4 is a 0 of f of x. So let's just, instead of me talking through that whole part, let me just show you how to take that problem and go straight to the math. I say -4 is a 0. The problem tells me -4 is a 0 of f of x. That means if I evaluate this at -4, I will get 0. 2, 7, -14, -40. 2 times -4 is -8. So we're going toward we know the answer is supposed to be 0, right? And it has to be, because they told us it's a factor. They told me when I plug in -4, I get 0. -1 times -4 is 4. -14 plus 4, remember these are all pluses again, is -10. -10 times -4 is positive 40. -40 plus 40 is 0. So I have factored f of x, and that will divide into what? X minus c. They told me -4 is a 0, which means x minus negative 4 is a factor. And what is that factor when I divide by that? What's left over? Well, the starter is a cubic, so then my coefficients down here represent the x squared term, the x term, and the constant term. 2x squared minus x minus 10. And then does that factor, obviously we can clean up on the first factor a little bit. Minus negative is just plus. And then 2x squared minus x minus 10. If you want, try to follow along with me here. So that leading coefficient is not 1, but it is 2. The only way I'm going to get 2x squared is if one of the coefficients, if my breakdown into binomials, one of them is 2x and one of them is x. All right? The last term has to multiply to negative 10. So two numbers that multiply to negative 10. Well, that's either going to be negative 10 and 2, or negative 10 and 1, or negative 5 and 2. In this one, when I multiply to get that negative 5 and positive 2, I need to make sure that I add to a difference of negative 1. So that means what? Well, if I break down, I want to multiply to negative 10. If I do, if it works out like this, where it's 2x minus 5 times x plus 2, do I get back where I started? 2x times x, 2x squared. 2x times 2 is positive 4x. Negative 5 times x is negative 5x. Negative 5x plus 4x is negative x. Negative 5 times positive 2 is negative 10. So I did it. You can do bottoms up there. You can do quadratic equation. You can solve them any way you want to. But what I did is it's mainly just a guess and check or reverse FOIL. And then the next part, solve the equation that we just did. Well, I know that breaks into x plus 4 times 2x minus 5 times x plus 2 equal to 0. If stuff's multiplied together to equal 0, then one of them is 0. 2x minus 5 is 0. So 2x is 5. And then again, the goal, x by itself. X is 5 halves. And then that last one, x plus 2, is 0. X is negative 2. So what are my solutions? Ooh, that looks like a man with an overgrown nose. That's much better. What are my solutions here? They are negative 4, negative 2, and 5 halves. And now the last page, we're going the opposite direction. If you are told a polynomial function has these numbers as zeros, they want you to find the polynomial function. So the zeros they gave us are 8, 2 plus 5i, 2 minus 5i. Now, here's the nice part about these zeros. It turns out if your 0 is complex or rational, or sorry, irrational, then the pair, that zero's conjugate is also a 0 of the polynomial. So in this case, 2 plus 5i is a 0. 2 minus 5i also must be a 0. That doesn't work for real numbers, but it does work for complex numbers and irrational numbers. So I just want to make sure we're drawing the right conclusion from each of these. So if 8 is a 0, then that means the factor x minus 8 goes into the polynomial function that we are going to create. If 2 plus 5i is a 0, then x minus 2 plus 5i is a 0 of the polynomial I'm interested in. Distribute that minus, that'll get rid of that second brackets inside. Negative 2, x minus 2 minus 5i. And then x minus 2 minus 5i, which is x minus 2 plus 5i. So I now have 3 factors of a polynomial. So that means f of x must be x minus 8 times x minus 2 minus 5i times x minus 2 plus 5i. All right, and the problem is probably going to suggest that you multiply. Yeah, the problem is going to ask you to multiply all that together. All right, so these my two zeros that are complex. If you ever have complex conjugates, because that's what they are. What's different, the plus and the minus. When I multiply these together, it's going to multiply out all the imaginary parts. And all I'm going to be left with is terms that have non-imaginary coefficients. So I don't want to say cheat, but I am going to, instead of multiplying this first factor by the next, I'm going to multiply these two together first. I'm going to multiply the factors that have the complex numbers in them. So what do I get? Well, this is going to leave a whole bunch of terms. So let's just get them out of the way. X times x is x squared. X times negative 2 is negative 2x. X times 5i is 5xi. And then we go to the second term, negative 2 times x is negative 2x. Negative 2 times negative 2 is positive 4. Negative 2 times 5i is negative 10xi. Okay. And then lastly, negative 5i times x is negative 5xi. Negative 5i times negative 2 is positive 10xi. Negative 5i times 5i is negative 25i squared. All right. Now, combine like terms. And what are we going to find? Well, a lot of these terms actually zero out. So let's find those first. Negative 2x minus 2x more. That doesn't subtract. Positive plus 5xi minus 5xi. Yeah, that zeroes out. negative 10xi plus 10xi. Those zero out. Okay. And remember I said when you multiply these conjugates, you're going to end up with no imaginary numbers. Well, that's all the terms that have imaginary numbers except for the last one. But we know that I squared is negative 1. So on the next line, I've got x squared minus 2x plus 4 minus 25 times negative 1. Combine like terms, and what are we going to find? We're going to find x squared is by itself. Negative 2x minus 2x more is negative 4x. And I'm looking at plus 4. 25 times negative 1 is negative 25. Minus negative 25 is plus 25. X minus 8 times x squared minus 4x, and then 4 plus 25 is 29. Am I done? Not quite. The next one's going to be considerably easier because it's a binomial times a trinomial. What are we going to get? X times x squared is x cubed. X times negative 4x is negative 4x squared. X times 29 is 29x. Negative 8 times x squared is negative 8x squared. Negative 8 times negative 4x is 32x. Negative 8 times 29 is 2. Oh, not plus. Minus 232. All right. So any like terms in here? Yeah, there's no x cubes. There's not 2x cubes. I do have some x squared terms. Negative 4x squared minus 8 more gives me negative 12x squared. 29x plus 32 more is 61. And minus 232. So what have we done? We've kind of worked the opposite direction. Up until this problem, it's always been a case where they give you the function and they ask you to find the zeros. Well, now it's Jeopardy. They're going to give you the answer and then ask you what the question is. And that's what we did. And that's all of 2.3.